Welcome to our virtual class. This is Teacher Amy, your teacher for this day. Materials needed: your textbook and pencil. So please prepare. So once again, welcome. Before we begin with our lesson, think of this. Complete this sentence. What will happen next? If we turned off the water in the shower, the water will stop pouring. If the water stops pouring, what will happen next? Of course, we don't get wet anymore. Based on the statement, what do you think is our lesson? Exactly. You are thinking, what will happen next? So, what word describes this one? It's conclusion. Our lesson is all about draw inferences from data. So, as we go back to the previous statement, as you can see, we are trying to conclude something else. This conclusion refers to the word inferences from data. Later on, we will be understanding what is this inferences from data. Open your textbook on page 319 to page 326. Objectives. Number 1, make qualitative and quantitative inferences from a sample dataset. Number 2, make estimates about the population based on the sample dataset and assess whether the inferences are valid. Review. Please read with me. Sample. A set of individuals or objects collected or selected. Sample size is a count of individual samples or observations in any statistical setting, such as a scientific experiment or a public opinion survey. For each situation in the chart, choose the term that best corresponds to the situation. Population, representative sample, random sample, or sample. Situation. Students at your middle school are surveyed about their favorite beverage in the cafeteria menu. Number 1. 10 students sitting together at the table. What do you think? Does it describe population, representative sample, random sample, or sample? You have 5 seconds to think. Correct. It's a sample. Number 2. Every student who attends your middle school. Good job. It's a population. Number 3. 10 students whose names are chosen from a hat without looking that contains a number of tickets equal to the school's population, each one labeled with a student's name. Exactly. Random sample. Number 4. 50 town residents who are voters. Excellent. It's a representative sample. Now think you're ready enough for a new lesson this morning. It's an application to the basic knowledge of population, representative sample, random sample, and sample.
The students in Ms. Miller's class cast their votes in the school-wide vote for which color to paint the cafeteria walls. Based on the data, what might you conclude about how the rest of the school will vote?
How many students are in Miss Miller's class? How will you determine the number of students in the class? Of course, you will see the votes based on the colors. As you can see, count it all together, so you'll have 30 students. How many students voted for each color? You have colors blue, green, red, orange, and you have also yellow. So you will see blue 12, red 7, green 4, yellow 3, orange 4. What is the sample and the population in this problem? Look carefully in the problem. Exactly. The sample are the students and the population, all students in the school. Now, even though this is not a random sample, but it could be a representative sample. Why? Because most people picked blue, so it's likely the whole school will vote to paint the cafeteria blue. Did you get me? Looking back at the votes for new cafeteria color, how can you use the information to make conclusion? So it's simple. You will see which color comprises the greatest percent of the votes. So what's the inference of the data? It concludes that the school will vote to paint the cafeteria blue based on the ratio of the blue vote. Welcome to
examples to draw an inference. Think about this question during the lesson. Sasha is trying to convince her mother to change her bedtime on school nights. She gathers data on the average number of hours of sleep that a random sample of 7th grade students in her school get each night. Will Sasha be able to convince her mother to let her go to bed later? To answer this question, you need to think about how you can represent Sasha's data. Sasha decides to display the data she collected in a dot plot. Now she has a visual representation that she can use to describe the data. What do the dots in the dot plot represent? Each dot represents the number of hours of sleep per night for one of the students in Sasha's survey. Each point is an average number of hours for that student. How does Sasha's hours of sleep per night compare to most of her classmates? Next, you can draw a curve to see the distribution or shape of the data. An inference is a conclusion you make by interpreting data. Sasha infers that about half of the 7th graders in her school get between 9 and 9.5 hours of sleep each night, which is the same amount she gets per night. Sasha is drawing an inference about her entire class based on the data she collected in her survey. Her data shows that she gets about the same amount of sleep as most of the students in her class. Sorry, Sasha, you probably won't be able to convince your mom to let you go to bed later using the data you have.
I hope the video helped you understand example number 1. So in this problem, Sasha is trying to convince her mother to let her go to bed later. Now, what is the population Sasha is studying? Exactly, it's the 7th grade students. What is the sample size? So how are you going to determine the sample size? Is it here or here? This one. So this one. So by merely counting, we will arrive at the sample size at 25 students. Looking back at the dot plot that she collected in the data, the majority of the dots are on the center. See this one? Okay. With a short tail on either side. This means the majority of the data are centered around 9 and 9.5 hours. The spread ranges from 8 to 10.1 hours of sleep per night. So the shape of the distribution is what we called as bimodal. It has two peaks. So what inference can we put in this data? As you can see, inference is a conclusion made by interpreting this data. So if we interpret this data, so Sasha infers that half the 7th graders in her school get
ages of students at a party. And what I'm hoping to do in this video is get a little bit of practice interpreting this. And what I have here are 5 different statements. And I want you to look at these statements. Pause the video, look at these statements, and think about which of these, based on the information in the box and whiskers plot, which of these are for sure true, which of these are for sure false, and which of these we don't have enough information. It could go either way. All right, so let's work through these. So the first statement is that all of the students are less than 17 years old. Well, we see right over here that the maximum age, that's the right end of this right whisker, is 16. So it is the case that all of the students are less than 17 years old. So this is definitely going to be true. The next statement, at least 75% of the students are 10 years old or older. So when you look at this, this feels right because 10 is the value that is at the beginning of the second quartile. This is the second quartile right over there. And actually, let me do this in a different color. So this is the second quartile. So 25% of the value of the numbers are in the second, or roughly. Sometimes it's not exactly. So approximately, I'll say roughly 25% are going to be in this second quartile. Approximately 25% are going to be in the third quartile, and approximately 25% are going to be in the fourth quartile. So it seems reasonable for saying 10 years old or older that this is going to be true. In fact, you could even have a couple of values in the first quartile that are 10. But to make that a little bit more tangible, let's look at some. So I'm feeling good that this is true. But let's look at a few more examples to make this a little bit more concrete. So we don't know based on the information here exactly how many students are at the party. We'll have to construct some scenarios. So we could do a scenario. Let's see if we could do a scenario where, well, let's see if I can construct something where, let's see, the median is 13. We know that for sure. The median is 13. So if I have an odd number, I would have 13 in the middle, just like that. And maybe I have 3 on each side. And I'm just making that number up. I'm just trying to see what I can learn about different types of data sets that could be described by this box and whiskers plot. So 10 is going to be the middle of the bottom half. So that's 10 right over there. And 15 is going to be the middle of the top half. That's what this box and whiskers plot is telling us. And they, of course, tell us what the minimum is 7, and they tell us that the maximum is 16. So we know that's 7, and then that is 16. And then this right over here could be anything. It could be 10, it could be 11, it could be 12, it could be 13. It wouldn't change what these medians are. It wouldn't change this box and whiskers plot. Similarly, this could be 13, it could be 14, it could be 15. And so any of those values wouldn't change it. And so 75% are 10 or older. Well, this value, in this case, 6 out of 7 are 10 years old or older. And we could try it out with other scenarios where let's try to minimize the number of tens given this data set. Well, we could do something like, let's say that we have 8. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. And so here we know that the minimum is 7. We know that the maximum is 16. We know that the mean of these middle two values, we have an even number now. So the median is going to be the mean of these two values. So it's going to be the mean of this and this is going to be 13. And we know that the mean of this and this is going to be 10, and that the mean of this and this is going to be 15. So what could we construct? Well, actually, we don't even have to construct to answer this question. We know that this is going to have to be 10 or larger, and then all of these other things are going to be 10 or larger. So this is exactly 75%. Exactly 75%, if we assume that this is less than 10, are going to be 10 years old or older. So feeling very good about this one right over here. And actually, just to make this concrete, I'll put in some values here. This could be a 9 and an 11. This could be a 12 and a 14. This could be a 14 and a 16. Or it could be a 15 and a 15. You could think about it in any of those ways. But feeling very good that this is definitely going to be true based on the information given in this plot. Now they say there's only one 7-year-old at the party. One 7-year-old at the party. Well, this first possibility that we looked at, that was the case. There was only one 7-year-old at the party, and there was one 16-year-old at the party. And actually, that was the next statement. There's only one 16-year-old at the party. So both of these seem like we can definitely construct data that's consistent with this box and whiskers plot, where this is true. But could we construct one where it's not true? Well, sure. Let's imagine, let's see, we have our median at 13, and then we have, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is going to be the 10, the median of this bottom half. This is going to be 15. This is going to be 7. This is going to be 16. Well, this could also be 7. It doesn't have to be. It could be 7, 8, 9, or 10. This could also be 16. It doesn't have to be. It could be 15 as well. But just like that, I've constructed a data set, and these could be, this could be 10, 11, 12, 13. This could be 10, 11, 12, 13. This could be 13, 14, 15. This one also could be 13, 14, 15. But the simple thing is, or the basic idea here, I can have a data set where I have multiple 7s and multiple 16s, or I could have a data set where I only have one 7 or only one 16. So both of these statements, we just plain don't know. We just don't know. Now the next statement, exactly half the students are older than 13. Well, if you look at this possibility up here, we saw that 3 out of the 7 are older than 13. So that's not exactly half. 3 sevenths is not 1/2. But in this one over here, we did see that exactly half are older than 13. In fact, if you're saying exactly half, well, in this one we're saying that exactly half are older than 13. We have an even number right over here, and so it is exactly half. So it's possible that it's true, it's possible that it's not true based on the information given. We once again do not know. Anyway, hopefully you found this interesting. This is the whole point of me doing this is, when you look at statistics, sometimes it's easy to kind of say, okay, I think it roughly means that, and that's sometimes okay. But it's very important to think about what types of actual statements you can make and what you can't make. And it's very important when you're looking at statistics to say, well, you know what? I just don't know that the data actually is not telling me that thing for sure.
Margot and Ravi are also trying to get their parents to let them stay up later. They collect data about the number of hours of sleep that a random sample of 7th graders gets each night. The 2 box plots show their data. Do Margot's and Ravi's data support Sasha's inference that most 7th graders in her school get between 9 and 9.5 hours of sleep each night?
So comparing this one to our problem number 2, it was Margot who suggested Sasha to use the mean and the median. So in this problem number 3, it's his friend now, also Ravi, and him also trying to convince their parents that they will stay up also later. Now, using the box plot, we are supposed to answer the question, does it support to Sasha's inference that the 7th graders has between 9 and 9.5 hours of sleep each night. So if this is the median in this data, median along 9 and 1/4 hours of sleep each night. Go. Analyzing the Margus data and Ravis data. Margus data on the top and Ravis data down. The ranges and the Margus data ranging from 9 to 9.75, while Ravis data 8.75 to 10. Whose sample has the most variability? Of course, its Ravis sample is larger than the ones in Margot's sample. So why is it important that Ravi and Margot's data support Sasha's data? Simply, it means that they each accurately sample the same population. So, looking back to our problem, what is the population? It's the 7th graders. So, being able to say that the 3 independent random samples of 7th graders said the same thing adds validity to the inference. The median time, this one here, at 9 and 1/4 hours in each random sample. However, based on the box plot, Margot and Ravi can infer that less than half of 7th graders get between 9 and 9.5 hours of sleep each night.
Derek is writing a report on cell phone usage. He collects data from a random sample of 7th graders in his school and finds that 16 out of 20 7th graders have cell phones. If there are 290 7th graders in his school, estimate the number of 7th graders that have cell phones.
So, looking at the problem, what is given? Yes, it is. There are 16 out of 20 7th graders have cell phones. What else? There are 290 7th graders in his school. What have you learned before that helps you set up the proportion in this problem? It's the equivalent ratios. So is there another way to solve this example? Yes. You could find out what percent of 7th graders in the samples have cell phones and multiply that by the total number of 7th graders to get the same answer. So what is the most important assumption to make when using a sample to make an estimate? Because the problem is asking for estimate the number of 7th graders who have cell phones. The answer is, it is important to think that the sample accurately represents the population. So what would happen if the sample were not represented of the population? Exactly, the inference or conclusion would be likely incorrect. So in this problem, we're going to write and solve a proportion to estimate the number of 7th graders who have a cell phone. So let's see, be the 7th graders with cell phone. Now we're going to make a proportion, whereas 7th graders with cell phones in sample all over the number of 7th graders in samples is equals to the 7th graders with cell phones in school over the number of 7th graders in school. How does it look like? So you will see 16 over 20 is equals to C, the cell phone, all over 290. Multiplying both sides by 290, so you will arrive C is equals to 232. So what inference can you make out of the solution? So based on the sample, about 232 7th graders in Derek's school have cell phones. Why is it important to analyze data both visually and quantitatively? The two methods serves as a way to check the other. One gives you a quick visual idea of what the data look like, but the other actually gives you precise numbers that can be tested against the numbers. So how valid would an inference be if the data used for that inference came from a non-random sample? The inference would be invalid in terms of representing the population. It might be valid in terms of representing a portion of population.
I hope you find this lesson interesting and understandable. See you in the next episode of the lesson.